This lecture will be about descriptive statistics. How do I take a raw, inert table of data and describe the data in such a way that key characteristics emerge? How do I work with the data set so that what's important jumps out, so that I see the dimensions which I should focus on? An overview of this lecture includes the following points: the purpose of descriptive statistics, viewing data, alternative ways of viewing data, summarizing data, variability in data, and other summary measures which are important in describing this data set. Descriptive statistics. How do I portray and summarize a set of data so that its key characteristics become evident? Once again, I want to take this toad, this rather ugly data set, and turn it into a prince or princess that has beauty to it. Beauty in the sense that key characteristics come out. Now, I don't want to overly romanticize statistics, but on the other hand, when it's done right, insights can be generated and business decisions can be made, which are dramatic improvements over not having the capability of doing the analysis. And this is what we stressed earlier, that competitive advantage has to do with knowing how to work with the data set, one dimension of competitive advantage. How do I transform raw, inert data into useful, refined information? Descriptive statistics tries to take this to a certain first step, and this is what we want to discuss in this lecture. First of all, let's talk about viewing data. And with viewing data, I want to discuss with you bar charts and histograms. I want to discuss contingency tables and crosstabs. I want to discuss scattergrams, and then present a little bit of information on time series data. Let's start with bar charts and histograms. I've drawn on this whiteboard an example of a bar chart, an example of a histogram. A bar chart takes data such as, here is the 3 film studios, MGM, Fox, and Disney. And now I want to somehow portray how many films they did in a year. The height of the bar relates to the number of films. In this case, I'll give Disney a larger number of films than Fox or MGM. And this might be 12, this might be 18, this might be 25. What I've taken here is, for a qualitative measurement, a qualitative variable that I'm looking at, I am providing a measure of the frequency, the number of films. Now, there's a slight distinction between a bar chart and a histogram. In a histogram, typically I start out with a quantitative variable. I start out with perhaps salary levels. And let's say we're talking about executive MBA students or whatever. And I'm trying now to portray their salary level. Executive MBA students are full-time working students who come back to school. And let's say in this particular population, I'm ranging from $80,000 to $120,000. They tend to do quite well. And I'm trying to portray the frequency or the probability. Notice I can either count the number of films here like a bar chart for qualitative variables, or I can provide a percentage likelihood, in this case for a quantitative variable which relates to salary. So here, $80,000, I have 10%. In the range at $90,000, I have 20%. $100,000, I have 30% of my population, and then I have 20 and 20 for each of $110,000 and $120,000. The notion here is that I want to try to visualize how these are distributed. I want to get a picture as to the relative likelihood of these classifications. Once again, bar charts, more nominal data. Quantitative variables, we tend to call that a histogram. So that's the distinction between a bar chart and a histogram. Now, let me talk next to you about contingency tables and crosstabs. The best way to do this is to go back to a classical example out of Ben Franklin's autobiography. Let me go back a ways to give you a sense of an old-time crosstab, and then I'll talk about crosstabs in today's world. If you recall from Ben Franklin's autobiography, he had a very simple goal for himself, and the goal was that he wanted to become perfect. So what he did was he identified 13 virtues. And some of them might be, remember, this is the 18th century, so temperance, silence, order, which meant getting things in their place, whipping things in line, papers and people, and getting things organized. And then he had 12, and I guess, as I recall, someone said that you should add a third one, really, Ben. You should add humility at the bottom. And he said, all right, I'll add that one. So he had a list of 13 virtues. And what he would do is he would focus on a virtue a week. 1 week he would devote to the virtue of temperance. The next week was silence. So this way, once a season, you would rotate each through these 13 virtues, almost like the virtue of the week. And when I completed 13 weeks, I would start over again. And what he did is he would, for Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday, track the number of times he violated this virtue. And if you recall, so for example, if he should have been silent and he spoke on Tuesday, he would reflect at the end of the day and track that, and mark that, and keep a record of, in a sense, a cross-tabulation by day, by virtue. And he would look at this pattern. Now, it turns out, if you recall, in Franklin's autobiography, what he says, when he came to this question of order, this virtue of order, his matrix, his crosstab matrix, and we call this a crosstab matrix, was so busy. There were so many marks where he had violated order, where he was not able to put his world together, that he said he almost gave up this quest, because this virtue discouraged him so much that he almost gave up his quest to become perfect. Now, this is an example of a crosstabulation of violation by virtue. Now, in business, we love to do crosstabs. And the crosstabs means I have 2 dimensions, and I'm tracking attendance by sex of a baseball game or whatever. I take 2 dimensions, and I cross-tabulate the number of occurrences for each of those characterizations. So a contingency table or a cross-tabulation is another means by which we can view or get our hands around this data so that its characteristics start to emerge. Now, also, we like to do in business what are called scattergrams. Let me show you an example of a scattergram. Now, when students try to do well in grades, and they try to generate what we call a GPA, a grade point average. And I may start to list some students down here. And I may put GPAs here of 3.9, which is a good GPA. Usually 4.0 is tops, 3.5, 3.1, 2.5, and 3.9. So here I have grade point averages for 5 students. Well, then what I like to say to students is that you may also want to generate an FPA. An FPA. And here a student might have 2.2, 2.9, 3.2, 4.0, and 4.0. Now, typically they say at this point, well, what's an FPA? I know what a GPA is, grade point average, but what's an FPA? And I tell them an FPA is a fun point average. You know, and you're trying to produce grades as well as fun. I mean, for some students, going back to school is, you know, particularly MBAs, there's a major social dimension, even undergraduates. Oftentimes they're trying to generate FPA and CPAs. They might say they could, or FPAs and GPAs. I mentioned CPAs. They may also have a career point average as to how far along they're pushing their career. Now, I have FPAs and GPAs. What I could do, if I wanted to develop a scatter plot for these, what I could do would be to start to plot these 2 dimensions. On one axis, I might put the GPA. On the other axis, I might put the FPA. So I'd go ahead and start plotting these points. Here's 3.9 GPA. It goes with a 2.2 FPA. And here's 3.5 GPA goes with 2.9. In general, if I go with a lower GPA, I go with a slightly higher FPA. I'm able to produce more fun. In fact, if you draw a point like this, draw these points, you might get something that looks like this. A curve which turns downward towards the axis, is concave downward. We call this a production curve in production, where I'm trying to produce 2 quantities, grades and fun, and they're kind of competing against each other. Now, I want you to notice one thing. As I look at this data set, here comes person E with a GPA of 3.9 and an FPA of 4.0. This person is outside the curve. Now, we call this person, as we mentioned earlier, an outlier. Somehow this person has been able to break out of this scatter mode. And all these points that I plot here are called a scattergram. A scattergram plots points along 2 dimensions and then tries to fit the data in some way. When we study regression later on in the course, we'll give you illustrations as to how regression models work with data points. But the point I want to make here is that here's a scattergram, and here is someone who is an outlier, who's broken out of the production mode, somehow figured out how to produce both of these dimensions very effectively. And as I said earlier, we may want to pay attention to such a person. He's figured something out here, or she's figured something out that enables her to be able to operate out here. Sometimes companies operate in this mode, organizations. Somehow they figure out how to operate outside of the pack. They're doing something. There's something special, whether it be a leader, whether it be some technology which is so proprietary that people can't compete effectively. They've moved outside the curve. They've moved outside the scattergram, and here we have this outlier. So we have bar charts and histograms, we have contingency tables, we have scattergrams. We also have time series data. Now, time series data is something which is not overly complicated. Let me just remind you what that's about. With time series data, I typically want to plot movement of some variable across the dimension of time. So here I might have share price. And let's say we take a company like a Netscape, which is involved in the World Wide Web. And here I have time. And the graph I'm drawing bears no semblance to reality, except you can see various dimensions occur. It may be issued, and then it may take off, and then the competitive threat may appear to be particularly strong. Somebody else comes at it, and then it may get an alliance with a major corporation, and then the stock market may view that up. And oftentimes when we do time series, where we plot data by the day or the week, sometimes time series, these are daily hash marks, sometimes they're weekly hash marks. Sometimes if I'm looking at long time series like quarters or years, it may cut across 10, 20 years of data. So the measurement, the intervals here can vary substantially based upon the perspective that I want to take, short run or long run. But the point I want to stress is that in time series data, we're plotting across this very important dimension of time. We're measuring, in this case, share price. And what we're doing is we're trying to visualize what caused some of these events. What triggered this upturn, or we're trying to make sense out of this data in some other way. And lots of people spend time looking at charts and time series graphics, and there's debates as to how useful it is. But certainly, at least at this level, it's useful to be able to see these major turns and events which related to those major turns. So, related to summarizing data, once again, bar charts, histograms, contingency tables, crosstabs, scattergrams, time series. These are four of the ways in which we tend to want to view data, to try to make sense out of data, to make the data come alive, to describe the data, descriptive statistics. Now, there are many other ways to view data. And there's ways, some people view data in 3 dimensions and spin it around, I'm only presenting you with 4 of the more common ways of looking at data. You have in your handout, in your graphic, a Dodger attendance histogram. We've seen this one before. That's another example of a histogram whereby I look at the data set and I portray frequency of attendees. How many people are going to 0 to 2 games? How many people are going to 2 to 4 games? How many people are going to 34 games, 35 games? And the height of the bar pictures to me the frequency, the number of people that fit in that category. And as I said, sometimes looking at data like this, you can see classes of, in this case, attendees or fans. Regular fans who attend a game or 2 or 3 a season, and season ticket holders, or what we might call super fans. Because season ticket holders may not be super fans. They may just simply hold season tickets to give out to other people. But these people who attend 30, 35 games would be considered super fans. Now, of course, if you get people going to 70 games a year or 75 games a year, you may have fanatics, people who we hear about people like this that are so devoted to an enterprise or venture that they are outliers. They're way outliers. That they're way outside of the normal descriptive analysis. Let's next talk about summarizing data. Summarizing data, and here I want to cover and make clear to you the distinction between a population parameter and a sample statistic. I want to talk about estimators. I want to talk about means, medians, and modes. I want to talk about percentiles and box plots. And finally, I want to discuss a cumulative frequency graph, also known as an ogive. Let's cover each of these points in some detail, because here the purpose, once again, is to summarize the data. Summarization is selecting one or more values to represent the entire data set. When I'm summarizing a data set, I'm picking a very select value to say this describes the data. I may pick more than one, but it's usually a small number of values to try to describe the data. And we'll give some illustrations of this as we go on. Now, let me distinguish between a population parameter. You can always think of it this way: PP, population parameter, and sample statistic, SS. So there's some alliteration here that's going on. A population parameter is a numerical measure for the entire population, for all possible Dodger fans, let's say, or all possible customers of the teaching company, or all possible purchasers of my exercise equipment. A statistic is a numerical measure of a sample. Normally, we can't get our hands around the entire population. I don't know how everyone is going to vote on this particular ballot issue. So what I have to do is go out and try to get a sample that gives me some sense of what percentage of people are going to vote for my ballot issue. That's a sample statistic, because that's all I can get at usually. The great Platonic parameter outside the cave, I usually don't get at. I have to work inside the cave and try to deal with some type of sample statistic, which gives me hopefully some approximation as to what the true population parameter is. And if I do things correctly, I can speak with some confidence as to what the population parameter is. So let me abstract this for you. Let me give you a picture as to what we're talking about here. So down here in quote-unquote the real world, I have lots of, say, people. I have lots of customers. I have lots of fans that are attending the ballpark or whatever. And this is my population. Up here, what I can't get to, I cannot reach all these people. So what I have to do is I have to come up here and construct a sample. And I pick some of these people to be my sample, selected sample. And once again, for a sample, I get a statistic like the average age of my customer base. For a population, I have a parameter, which is the real average age of my customer base, but I don't know it. And I can't survey all my customers. I can't get at them. So I construct some type of sample to give me a statistic that's associated with that parameter. This distinction of a sample statistic versus a population parameter we'll see several times as we go through this course. So I want to be sure that that's clear to you. I may, for example, and in my population parameter, I may call it mu. Mu is typically, this is a Greek letter mu, which deals with the average age of my customer base. I want to try to estimate mu. I may calculate something called x bar. X bar is a sample statistic that tries to estimate this population parameter mu. If I do a good job, I'll have a good estimator. Good estimate. If I do a poor job, I may or may not get close to what mu is all about. But that's the intent. X bar is said to be an estimate of mu. It's said to be an estimate of mu. Now, later on, we'll talk about bias, potential bias in the estimate, and how to try to minimize that. But this is what we're doing when we're talking about summarizing data. Now, let me give you an illustration of some summary measures. I have on the board behind me some information. Well, before I go to that, let me first of all calculate some numbers here. What I have here is a customer base. I have 5 customers, 1, 2, 3, 4, 5, and this is a very small sample. And if we get a very small sample, the odds are that it's not a very good estimate of my true population parameter. But that's one of the things we'll talk about in subsequent lectures. How large a sample size do I need to take to be able to have confidence that I'm really trying to get at that population parameter effectively, that I'm reaching it? Now, I have age of my customer base. And this, for argument's sake, let's say this is all dummied up data. It's not real data. Let's say this is the teaching company. And here's my customer base. I've got the first person is 30 years old, the second person is 30 years old, the third person is 40 years old, the fourth person is 50 years old, and then I have a 100-year-old customer that comes in, okay? A centenarian. Now, I may want to work with this data in some way. And one thing I might want to do is calculate as a summary measure a mean. And the mean is simply the arithmetic average. I add all these up and average them out. And if you did that, and I'll do it quickly, this is 30, 60, 100, 150, 250, divided by 5 is 50. So the mean age is 50 years old. Now, I want you to notice something, that with this sample, the mean may not be a good measure, because this 100-year-old person is exerting a great deal of influence on the data. It may be having undue influence in dragging up the mean. So you have to be aware of such dynamics when you're analyzing data. Another summary measure that we use commonly might be the median. And many of you know that the median is simply the middle data point. Here, the middle data point is point number 3. I've ranked ordered this data set so that the median is 40. It's easy to see it would be the one in the middle, the median value. So the median is 40, and the mode of this data set is the most common data point. In this case, the most common data point is 30. 30 appears twice, the other values appear just once. Notice that the summary measure that I pick has a great impact on what number I use to represent the data. But the point here is that with summarization, I'm trying to pick one value which represents the data effectively. And we'll talk more about this as we go on in the course as to selecting a good, unbiased sample statistic to represent the population parameter. I want to talk next about a box plot. Now you'll see these appear sometimes, and I want to be sure that you understand how to read these, because one of the things we want to do in this class is to just give you a comfort level with statistical analysis that you may not have. And it's like a language, you know, like any other subject, you start to hear more and more about it, and just able to do things more effectively and work in that domain once you get comfortable with the domain. And I want to do that for you here. I have an aunt in Portland, Oregon, that when I go to see her, she always asks, she serves me a cup of tea, and then or coffee, and but very quickly, she brings out annual reports from companies that she's investing in because she wants to understand more about the annual reports. And she has a question about this accounting procedure or that accounting procedure. And there's a language here, just like accounting. Statistics and data analysis and probability has a language. And as you get more familiar with this, you'll feel more comfortable, more in control as to what's occurring. And that's one of the key things, key objectives that we want to achieve in this course. Now, a box plot looks like this. A box plot, it might not surprise you, has a box in it, and it has a line through the box, and then it has whiskers. It has whiskers going out of the box. Now, let me describe to you what the box plot looks like, because once again, this is a summary device for data. The line here in the middle, the value associated with that is the median value. Over here in the example we gave of teaching company customers, the median was 40. Now, the top of the box is the 75th percentile, and I'll explain that in a minute. The bottom of the box is the 25th percentile. I'll spell out percentile. I wrote percents, but let's write percentile there. And what that means is that 75% of my observations, 70% of my data, essentially are less than this value. 25% are less than this value, the 25th percentile. So it kind of shows me where my middle 50% are. Where is the middle 50% of my data between the 25th percentile and the 75th percentile? Between the bottom of my box and the top of my box. Now, then I've got the whiskers that go beyond that, and I may have a point up here which gives me the largest non-outlier, and a point down here which gives me the smallest non-outlier. Then I may have some outliers, which usually are designated by a star, which I'm sure in this data set on the teaching company that the 100-year-old person would be construed as an outlier. Although I'm not sure, you know, I don't know the data of the teaching company. But the point is that this person would be off the traditional box plot. So notice that the box plot gives me a very convenient way of summarizing this data pictorially, and it gives me a representation of where my data lies. Now finally, what I want to do is discuss with you what is called an ogive. It's also known as a cumulative frequency graph. Let's go back to the data which I showed earlier, where I had 5 customers of the teaching company and their ages. What a ogive does is that it shows, as I go to the right, a percentage of people that are less than any given age, cumulatively. For example, here I have 40% of the people age 30 or less. So here, when I go up to 30, nobody's there. But when I hit 30, I have 40% of the people, 2/5, that are less than 30. And then I stay at 40% until I go to 40, where I pick up another 20%, 1/5 of the data set. And I stay there until I go to 50, where I pick up another 20%. Or I have 80% of my people now that are less than 50 years old. And then I have to stay all the way at 80% for this data set till I go way out to pick up my 100-year-old man or woman. There's when I move up to 100% of my data is less than 100 years of age. So the ogive for variables such as this, which these are discrete data, particularly we tend to measure age in discrete years, you know, 1 through 100 or 1 through 120. It's not necessarily continuous. Is a series of steps that I step up to build my ogive. Now, if I have continuous data, an ogive tends to look more continuous, a smoother curve. But with discrete data, the ogive tends to step up till I get a picture of what percentage of my population of interest or sample, if I'm developing off of sample data, is less than a given age. So to summarizing data, we've talked about ways of developing sample statistics, the difference between a sample statistic and a population parameter. We've talked about estimators. Some of them are good, some of them are not so good, and we'll discuss that in much more detail. We talked about mean, medians, and modes, and percentiles, and box plots, and cumulative frequency graphs, also known as ogives. The next thing I'd like to cover with you is variability. Now, variability has a central role in statistical analysis. If everything was the same, if there were no difference among responses, statistics might not be that interesting. But it becomes interesting because we do have variability, and we have to kind of get our hands around variability. I want to mention to you the traditional choice for measuring variability, the standard deviation. What is it? Why is it important? And then I want to talk to you about some way out events. Because although we tend to think, as you'll see, of data within a certain range, maybe measured in terms of standard deviations, which has to do with how, on average, spread out the data are, in some cases, we have some way out events occurring, and some of those things become quite interesting to us. Now, as far as the central role of variability, I don't care whether you're describing your children's personalities or whether you're describing age differences or income differences. Variability is kind of what makes things interesting as far as analysis is concerned. Variability in stock price as a percentage of earnings or as a multiple of earnings. All these things kind of give richness to life and what life is about. Let me talk to you about the standard deviation and try to build some intuition about the standard deviation as to why we like to use the standard deviation. The standard deviation is given by the following relationship, and then I'll illustrate this. Normally we call it S for a sample, and it is, now we're going to get into a little mathematics, so we have to sum up, and this means sum up, sigma, it's the Greek letter sigma, xi minus x bar, square it, and divide by n minus 1. Now, don't worry if your mathematics is a little rusty. We'll try to refresh your mind on some of these things. What's going on here is the following. Let's look at two mutual funds. Here's mutual fund A. And B. Now let me measure the return from these mutual funds for years going forward. Let's say that I put year here x, year x plus 1, x plus 2. And I'm measuring the performance of these mutual funds. And the first year, mutual fund A returns 15%, 5% in the second year, 15% in the third year, and 5%, let's say, in the fourth year. Let me stop right there, okay? Whereas the second mutual fund gives me a minus 10%, a minus 10%, a minus 10%, and then explodes with a 70% return in year 4. Now, notice that if I calculate x bar for each of these, x bar is the average return. This adds up to 40, and divide by 4, I get 10% average return. This one also adds up to 40, 70 minus 10 minus 10 minus 10 is 40, divided by 4 is also 10%. So if I were to use the mean to describe these two data sets, they look identical. So what I do is I also say I want to know how varied these are from the mean. How varied are these returns from this mean of x bar? So what I'm doing when I'm calculating the standard deviation is that I am subtracting each of these values, 15% from minus 10, which is the mean. And I'm adding them all up, and I'm dividing by n minus 1, and we'll talk about why it's n minus 1 as opposed to n in another lecture. It has to do with the concept of what we call degrees of freedom, which we'll deal with. And then I'm taking a square root. Now, I'll leave you to do this on your own, to check to see if you can do this, but I'll give you the answers here. S for this data set is 3.3%, and S for this other data set, the more varied one, portfolio B or mutual fund B, is 40%. Notice that the 40% reflects the fact that this data is moving around a lot, whereas the 3.3% shows that this data is closer to the mean. So if you don't want to do the mathematics, build the intuition of what the standard deviation is about. And the intuition of the standard deviation has to do with how close are each of these data points on average to the mean. That's what we're trying to achieve when we calculate a standard deviation. And you may hear a lot about plus or minus 2 standard deviations or 3 standard deviations. What that means is that most observations for most data tend to be within 2 or 3 standard deviations of the mean. Now, in some cases, we get some way out events, like the crash of a stock market might be 20 standard deviations away from the mean. Or we talk about the average number of times that a couple might have sexual relations. And then we have somebody, and I had this experience in my life, come up to me and talk when I first got married about how often they were having sex. They wanted me to tell them whether they were abnormal or not. And I really didn't know, but they were having sex quite frequently. They were way out, quote unquote. Now, whether in fact it was the truth or whether they were exaggerating, you know, I'll leave that to your judgment. But there are some events which occur which are way out. But in general, the standard deviation gives us some sense of how close the data set is to the mean. Now, finally, I want to cover other summary measures with you. There are other measures besides the mean and standard deviation that we use to summarize a data set. One is skewness of the data. And the other is kurtosis. Let me spend just a couple minutes on each of these. When I talk about a data set being skewed, it means that if I plot the data, it tends to have a tail to it, like this. That it's not symmetrical. The curve goes up, and this is frequency, and this is some other measure. Maybe it's revenues. Maybe this is a distribution of films, let's say, of domestic box office in the film market. I may have a few films that really do phenomenally well. And we're going to talk about a film model in another lecture, but I'll open it up right here to say that most films might perform down here in this lower level where the bulk of the curve is, but it's skewed to the right. It's skewed to the right. A right-hand skew means the tail goes off to the right. A left-hand skew would mean the tail would go off to the left. That it would be the opposite of this, that the bulk of the data might be up here, and then I tail it off to the right. So I have a tail which heads off to the left. An example might be, I like to tell students, I hope this is how their grade distribution looks like. Most people are doing very well. There's a few people having trouble that are skewed off to the left. So I have left-hand tail and right-hand tail skewness. And then the last thing I want to mention to you is kurtosis. No, that's not bad breath. It's a different type of thing. It's not halitosis, it's kurtosis. And what kurtosis has to do with whether or not the distribution is peaked or whether it's flat. If my data looks peaked, like this, tight together, we call this leptokurtic. If it's spread out, so it looks like this, where the distribution is pulled out and stretched, we call that platykurtic. Now, one final example, and that is that if my employees' salaries, for example, are tight together, if they're bunched together, it would be leptokurtic, my salary. So on the other hand, if I had a distribution that would spread out, my CEO salary is way out over here, my salary is flattened out, spread out, it would be platykurtic. It would be flat, so it would be spread out more. These are some other summary measures that we employ to be able to describe data. But again, the purpose of descriptive statistics, whether we're talking about summary measures in the form of means or medians or modes or standard deviations, or whether we're talking about skewness, left-hand tailed skewed or right-hand tailed skewed, or whether we're talking about the height of the distribution, whether it's flat or whether it's spread out. The purpose of descriptive statistics is to portray and summarize a set of data so that its key characteristics become evident. And these are some of the techniques we use that I've described to you to take inert data tables and to bring them to life, to add meaning to them, to make them come alive so that key characteristics can come out and that you will see meaning and life in the data.